Hi, and welcome to the Earth Science Classroom. Today, looking at floating continents, plate tectonics, looking at the idea of how these huge continental plates, which include the crust, lithosphere, are technically floating on the mantle. And this is in reference to a principle called isostasy. It is in geophysics, and it's a term that we can relate to multiple fundamental mechanisms on the Earth's surface, ice sheets and ice ages, and how ice covers the Earth's surface and then retreats, looking at mountain ranges and how thick they are, where the moho is, how deep moho is, and why these larger continents would sink down deeper. And we're going to look at, well, this will be part one. So part one will cover pretty much Archimedes and his principle. Look at the definitions, okay, and also the densities, and discuss a little bit about India and the two surveyors. Okay, that's the first part. Second part, we'll get on to the flexure and the isostatic rebound and different examples. All right, so guys, join us now for this new video. All right, so this is part one, right? So we're going to look at the background and where isostasy kind of took place and how we figured it out and who figured it out. Now, this dates back to ancient Greece. Now, anyone can see that if you throw a heavy stone into a pond or a lake, that it's going to sink. Or if you swim in the ocean, there's a chance you can sink if you're not going to swim or tread water. Anything heavy in water is going to have that effect where it's going to sink to a certain depth, maybe down to the bottom of the lake or just to a few feet down, depends on the object. So obviously gravity is going to keep us on the surface, and it's a force of attraction based on the center of mass, which is the center of the Earth. Okay, but this is the buoyancy. So it's basically the science behind flotation, and if something floats or sinks, basically, or is it going to be in a state of equilibrium where it neither floats nor sinks or even moves up or sinks. It's an equilibrium, stays the same, or steady state. Okay, so the gentleman, the amazing person in ancient Greece that pioneered this idea, this principle, this scientific discipline, is a gentleman called Archimedes. And he did this in 287 to 212 BCE, so around over 2,000 years ago, or 2,200 years ago. And he constructed this formula based on basic math, basic physics of things that float or sink. So he observed that inside a fluid, okay, let's just say water for now, there you put a cylinder, you put a mass or an object of certain mass. Let's just put a mass n. There's going to be two forces that are applied or acting upon the object inside the fluid. There's going to be the force 1, which is the force of gravity, okay? And then there'll be also the force down here. This is F2. So F1 is obviously gravity and the mass, and so F1 would be obviously gravity acting upon it, plus the mass of the object, and we call this weight. So the weight of the object. And then F2 is going to be the force applied by the actual fluid itself, the fluid strength, the fluid force. And this is an upward force acting against the F1 force, the weight. So there's a battle between these two based on the object itself, and obviously the depth of the water, because with depth, or as depth increases, so does the pressure, because there's more of the fluid above it, so you get an increased what's called hydrostatic pressure. It's inside the Earth, it's called lithostatic pressure, but it increases with depth, same as our pressure and depth chart inside the Earth, which is shown in a different video if you want to check it out. So if the F1 weight is larger than the F2, it's going to sink. Okay, so, or if it's going to be the opposite, if the F1 force is less or lighter, then it's going to rise, because the F2 force is greater, and this is called the buoyancy force. So if you are able to swim on an ocean without, well, you can just basically lay in the ocean and not sink, then that means the water's buoyancy force is far greater than the weight of you in the water. The same applies to a cruise ship, an oil tanker, any kind of boat on the ocean or object on the ocean. It has to displace enough water that it's going to equalize out the pressure, and the buoyancy force would be enough that the object stays afloat. That's why you wonder why these massive mile-long oil tankers don't sink, because they are displacing enough water to equalize the pressure and create an equilibrium between the weight and the buoyancy force of the water. If you're a person who loves formulas and math and applying math into physics and science and chemistry, and you're just all about the calculus and function of this and function of that, then the pressure with depth is going to be P equals HPG, all right? And with the buoyancy force and something that's going to float, you're going to have the force of buoyancy equals the weight of force 1. So it basically equals out. Okay, no difference. All right. So this was Archimedes. This is over 2,000 years ago. This is amazing that he figured it out, and it's a principle that we use today in modern engineering, construction. Anything naval. Submarines and ballast tanks, and how they equalize the pressure and the air, and they can sink and rise. It's quite amazing how they've adapted this. So, long story short, how do we get from ancient Greek to our isostasy and plate tectonics? Now, don't forget, a plate is the crust, could be either ocean or continental, and tectonics would be basically the builder. It's the architect, basically, and also the lithosphere as well. Don't forget the MOHO, which is the line of discontinuity of that seismic wave that would change speed, increase velocity from the crust into the mantle. In this case, that is the upper mantle, which includes the lithosphere, which is solid, increased density as you go deeper, and then obviously into the asthenosphere, which is our weak layer, which has some magma and some fluid properties and some plastic nature in terms of the way it moves. And we have convection currents. Again, I have a whole video on this if you want to check it out. both of the upper mantle, asthenosphere, and crust lithosphere. So it is all about density. And density is mass over volume. So how dense things are, how closely packed things are within a given volume. And obviously different rocks, different materials have different densities. So the increased density is going to be more likely to sink, okay, within a fluid environment compared to a lower density material, which is likely to float. So against a fluid environment. So we know this based on Archimedes. Now, how does this relate to plates? Well, there is general densities of plates, but let's look at the classic example. This is how we kind of introduce this. The classic example of the flotation is the iceberg. Now, we all know the Titanic, classic example of, the unsinkable ship across the North Atlantic and encountering an iceberg, and the rest is history, or on a movie with Leo. But the iceberg has a classic example we can all kind of draw and appreciate. So here is our ocean, all right? And here's our iceberg. I'll just do it in black now. So we have this. There we go. All right, here's our iceberg. All right. So a ship that does not have sonar, does not have any kind of modern tech, would just basically see this part that is, above sea level. Okay. And they, oh, it's kind of small. They didn't know icebergs. But the rule of icebergs is you can only see above the water 10% of the mass of that iceberg. So 90% is basically underwater. Why? This is buoyancy. This is our Archimedes principle and our isostasy. Now, why ice floats is because when water does a phase change into solid ice, the chemical bonding actually increases the volume by about 9% from liquid, and that creates more gaps and space and voids in between the chemical bonds and the hydrogen and oxygen, thus making it slightly less dense. So ice is 0.91 grams per centimeter cubed. And we all know that density of water is around 1 gram per centimeter cubed. Thus, 0.91 is less dense than water. Thus, ice floats. Now we can get into the chemical structure of ice and water in a different video. Right now we can just visualize that this iceberg is lighter, is going to float. However, majority, 90%, is going to be under the surface of the water because of the mass, and it's going to sink down with a force 1 and then a force 2 up here, the buoyancy force. This is up here, down here. The depth of the bottom of the iceberg is called the compensation depth, where both pressures equalize, and thus that is the lowest point in which the iceberg can sink to. Now, if you added more ice to this iceberg, then it would sink a bit lower. Or if there is some kind of like sublimation, which is going to take away ice and form it straight into gas, and or it starts to melt into water on a sunny day. Perhaps it floats down down to the Newfoundland from a Labrador current. Then it's going to actually push up with less mass. So there's that balance, a very nice balance. Now we can apply this to our continents, our huge, massive continents. And that brings us to India. Now, India was part of the British Empire, the British Commonwealth, and the British went to India and started to basically say, hey, we're here now, we can help you run the country, and the rest is history, basically. But Britain sent over 2 surveyors, well, more than, but these 2 surveyors were the famous ones in terms of isostasy. They wanted to map and survey the northern part of India around the Himalayan mountains. And they used a plumb line. And this is to basically figure out the gravitational pull on the Earth and the direction, and basically to establish a vertical column between the hanging point and the Earth's center. So this is a good way to figure out where you are on the Earth and how high you are and elevation, and obviously the gradient. So the plumb line was used, and they basically surveyed this whole area, and there was a 177-meter error in their calculations or in their data. And these two gentlemen, named Airy and Pratt, both had kind of similar yet a little bit different theories onto why this error was there. Now, they thought it would be a larger error because of the gravitational anomaly of the Himalayan mountains. Himalayan mountains are such a large body of rock that they assumed it would be a larger error in their calculations due to the mountains being there. And they knew this from prior knowledge, like they found this in Peru as well with the Andes, that the Himalayan mountains would distort their data, but they didn't realize it was a little bit of distortion, only 179 meters, which is not too much, but enough to be visible in their data. So these two had conflicting and different theories as to why this error had occurred. Now, Airy's came first. This is in 1854. Now, Airy decided that there was a layer of lava. So I'm going to draw it out, basically. So so here's our columns of lithosphere, lithic columns. All right. And let's make this flat. There we go. And what he proposed was that there was the same densities of all these different columns. And the higher they are, the lower they go under surface into the lithosphere and into the asthenosphere, and they compensate. So the higher is, the more compensation there is deeper down to compensate for the mass, because it pushes it away and kind of like moves the denser material away, and it increases the force of buoyancy until it gets to an equilibrium, or what's called the compensation depth. So this is like Airy's idea, was that they're all the same. So all these columns are the same density. Let's just say it's 2.65 grams per centimeter cubed. And that the asthenosphere down here, the mantle down here, okay, was of a greater density, let's say 3.6. So we still have this agreed upon floating observation or conclusion or understanding, but Airy's was that the columns were the same density, and they had this kind of like lower down area corresponding to the elevation change on the surface. So the higher the elevation change, the more deeper it would sink down into the asthenosphere mantle to compensate for the compensation depth. And the material pushed this way, and the buoyancy force would be equalized. Okay. Now, Pratt had a similar idea, but Pratt was in 1855, a year later, or in the next year. His idea was that each of these columns were of different densities. However, the compensation level was all equal. There was no different depths according to how the different elevations on the surface is one thing. So the asthenosphere down here was just a consistent depth. And these were all different densities. So let's say 2.6, 3.1, 2.8, 4.2, 3.1, 2.5, like that. So each one was different. So there was varying densities horizontally along the crust that accounted for the change in elevation and why these mountains are so tall, and accounted for the gravitational anomalies. So that's what they're basically looking at when they're surveying with the plumb line. Gravitational anomalies is based on density, how density affects gravity. And gravity can either less mass or more mass, which would change, either be a positive or a negative gravitational anomaly based on the average. And you could see where there's lighter materials under the ground, salt dome, or greater densities under the ground, like, let's say, oil. Oil or gas, or not gas, oil or certain kinds of igneous rock, let's say granite pluton. Or looking at volcanoes, definitely looking at magma being a less dense material, magma coming up and rising in a magma chamber ready for an eruption, like with Yellowstone. So these, the plumb line or vertical distortion is going to show them this. Now, both these theories were agreed upon for the floating idea of buoyancy, but they do differ in their understanding of what happens underneath the crust. So Airy had root established, or we called it the lava, and Pratt was correct in that there are different densities in different parts of the crust. So they're both correct, but if we combine them, we get the idea of isostasy. So modern-day isostasy has been taken into account here based on the buoyancy and Airy and Pratt, and looking at, obviously, the terrain of the planet is a bunch of valleys and plains and mountains and areas of different elevations and gradients and slopes, and also different densities based on the composition of both the ocean and the continents. So you have the ocean being mostly basaltic, continent being mostly granitic. So, and obviously, density is going to increase with depth as well. But also, you have these elevation differences. Now, with the mountains here and here, and you have some valleys. Some valleys down here. Now, what you have is this corresponding compensation depth of the force of buoyancy and the amount of material, the dense material. So the average mantle is going to be like 3.4, whereas the average crust is going to be between 2.6 to 3. And you're going to have this lighter material floating on top, pretty much, of this plastic material. And it can also involve convection currents and upwellings and subduction zones and trenches, all that good stuff. But you also have this kind of like root, which is that increased larger area of material, light material, that's been sinking down, like in the iceberg, and it's the root of the mountain. And also you can anti-root on areas that are less elevation, so valleys or even ocean plates that are very thin compared to the continent, so 5 to 7 kilometers, with an average continent of between 25 and 35 kilometers. So you'll see that the MOHO, the composition level as well, is going to change under the mountains versus the valleys and ocean plates because of these root and anti-roots. So in conclusion, we started off with ancient Greece, Archimedes and buoyancy, the principle of which is force of buoyancy equals E, density, gravity, and the fluid volume. Then we go into India and Airy and Pratt, Airy being the lava and the root, and Pratt being different densities. And then combination, which is they both understand that they float, and looking at the seismic waves kind of confirm this with the root and anti-root underneath continents and valleys and oceans, and the idea and understanding of how continents both move and float at the same time in terms of the overall plate tectonics, the whole system, how it relates to subduction, how it relates to rifting, continental rifting, and also the changes on the surface due to weather and erosion, uplift and subsidence, and ice ages, and meteor crater impacts, all that good stuff. Guys, hope you enjoyed this video. Hope you liked it. If you're new to this, please subscribe and leave a comment. Always great to have new people join the channel. And hope you enjoyed this and look forward to more videos on Earth science.